Good afternoon. Now welcome in the second part of the stiffness matrix. Now in this part, we will see how to generate the stiffness matrix. So consider one structure as shown in the figure. And here there are four coordinates. And these four coordinates are numbered as this is one. Coordinate 1 is a force. Coordinate 2 is a moment. Coordinate 3 is also again a force. And coordinate 4 it is a moment. And here the span L1 is equals to L2. Then to generate the stiffness matrix, first of all, provide fixity. So that is here, this point provide fixity. That is one part. Second, okay. Now in this, for this particular structure, there are four coordinates are there. That is 1, 2, 3, 4. So therefore, the generated stiffness matrix, its size will be equal to 4 by 4. Now, since the size of the matrix is 4 by 4, so it is that there are four columns and four elements. 4 columns and 4 rows are there. Then this stiffness matrix will be generated column wise. Okay, it will generate column wise. So these are the 4 columns and these are the 4 rows are there. Okay, now first of all, we'll generate the first column of the stiffness matrix. That means we will determine what is this element K11, K21, then K31 and K41. Then after that, we will generate the second column, then third column and fourth column. So in this way, we will follow, or this is the procedure to follow the to generate the matrix, complete matrix. Then to generate the first column of the stiffness matrix, apply unit deformation at coordinate 1, because stiffness is what? In the case of stiffness, what is the force required to produce a unit deformation? So to generate the first column of the stiffness matrix, apply unit deformation at coordinate 1. Okay, now coordinate 1. What is coordinate 1? Coordinate 1 is a force. So here at this location, apply a force. Okay, and then after application of the force, first of all, what are the ends of the part? This is the first part. This end here and here. Provide fixity, provide restraint here first of all, and then apply the force here. Now, what is the magnitude of this force? Such that it should produce a unit deformation, or in other words, to produce a unit deformation, that delta equal to 1. How much force is required? Only that much force we have to apply here. So when the force is applied, which is producing unit deformation, then both part will deform. So as shown in the figure. So the first part, this will deform downward. So here we have provided fixity, and here it will be deformation equal to 1. So this is the deformation in the first part. And in the second part, this will be 0. And here it will be equal to 1. Now, this deformation of first part and second part, this will produce some internal forces. So that is shown separately in the first part and second part here. So this is the first part. Where the unit deformation is applied at this particular part. And this is at the same level. So this becomes a level difference. So it is called as the sinking of the support. This becomes sinking of the support. So here the end which is at a lower level. So at that place, it will be a sagging moment will be there. So it will be equal to 6 EI. This is a sinking moment. 6 EI delta divided by L1 square. But delta value is equals to 1. So how much moment will be there? It will be 6 EI upon L1 square. And moment produced at the far end, it is in the same sense, that is anti-clockwise, here also anti-clockwise, and magnitude same, it is 6 EI upon L1 square. So these are the sinking moment automatically developed at the ends. Now these sinking moments will produce a couple. Now this is a sinking moment. What is this thing? Direction anti-clockwise, and therefore whatever the resisting couple will be there, this is in the clockwise direction. So it is a couple, therefore forces will be magnitude same, direction opposite. So it is clockwise. So therefore, this is downward, this is upward. And this value is how much? Value of this force will be equal to imbalance moment divided by L span. So it is equals to 6 plus 6 because both are anti-clockwise. 6 plus 6, it is 12 EI upon L1 square divided by L. So it becomes 12 EI upon L1 cube will be this force, and this upward force will be again 12 EI upon L1 cube. Okay. So these are the internal forces in the first part. Similarly, internal forces in the second part. Okay, now second part, this end is at a lower level, this at the upper level. So this is lower level by an amount of equal to delta. The end which is at a lower level, so there it will, the moment, sinking moment is a sagging nature. So it is equal to 6 EI upon L2 square, 6 EI upon L2 square. And it is a clockwise moment. The moment produced at the far end is again a clockwise, the value same. It is 6 EI upon L2 square. Okay, now this will generate a reaction. So this is a clockwise moment. So resistant couple will be anti-clockwise. So this will be upward force, this will be downward force. What is the magnitude? It is M divided by L. What is M? 6 plus 6. It is 12 EI upon L1. So this is this 6 EI and this is, so 12 EI upon L2 square divided by L2. So it becomes a 12 EI upon L2 cube, and this will be 12 EI upon L2 cube. So these are the internal forces in the part number 2. And then we can write the elements in the first column. Okay. Now first element, what is K11? What is our K11? So here for the reference, I will this is our structure. This is element 1. So this is element 1. This is element 2 now. This is element 2. This is element 3. This is element 3 and this is element 4. Okay. Now K11. What is K11? Stiffness at 1. How to read this? Stiffness at 1 due to unit deformation at 1. How to read this? Stiffness at 2, coordinate 2, due to unit deformation at 1. How to read this? K31, stiffness at 3, due to unit deformation at 1. Now first is stiffness at 1 now. What is coordinate 1? Coordinate 1 is a force. Coordinate 1 is a force. So that means, so this is the location. So in the first part, this is the location, what is the force generate, and what is the force generate at the, in the part second. So in the part 1, what is the force generated? It is 12 EI L1 cube. And in the second part, again, 12 EI upon L2 cube. So this is downward, and assigned coordinate is also downward. Assigned coordinate here, it is also downward. So therefore, element will be positive. So this is in the first part, and this is the second part. So it is 12 plus 12, 24 EI upon, now substitute L2 equal to L1. So it is 24 EI upon L1 cube is the first element. Then element 2 now. No, okay, so stiffness at 2 now. Stiffness at 2. What is coordinate 2? Is a movement. Coordinate 2 is a movement, and it is a clockwise movement. So at 2, here at this location, what is the moment produced now? Okay, so here in the first part, anti-clockwise 6 EI L1 square. And in the second part, it is clockwise 6 EI upon L2 cube. Okay, and L1 equal to L2. So it becomes 0. Okay, so 6 EI L2 square in the first part, in second part, and 6 EI upon L1 square in the first part. So it becomes, since L1 is equal to L2, it will be equal to 0. Then K now 3,1. K 3,1 now. So what is our element 3? Element 3 is what? Okay, so element 1 is here, 2 is this, element 3 is this. So this is the element 3. Okay, so element 3 is a force now. Element 3 is a force. Now what is the location? Is this. This is the location. So in the second part only. So in the second part, what is the force generated? So what is force generated? 12 EI L2 cube. But it is upward. Force generated is upward, while as assigned coordinate is downward. So therefore element will be negative. Element will be negative. So this is minus 12 EI upon L2 cube, and substitute L2 equal to L1. And then K41. K41. What is coordinate 4? Coordinate 4 is this. It is a moment. So what is the moment produced at this point? So what is the moment produced? It is 6 EI upon L2 square. 6 EI upon L2 square. And it is clockwise, and assigned direction is also a clockwise. In the same sense, whatever the force produced and assigned coordinate, if it is in the same direction, then element will be positive. Then this will be positive 6 EI divided by L2 cube. I am substitute L2 equal to L1. Okay, we are substituting L2 equal to L1 so that all the elements are in terms of L1 only. Okay, so this is the first element, second element, third element, and fourth element in the first column of the stiffness matrix. Okay, then we'll go for second column of the stiffness matrix. Then write important line. First of all, to generate second column of the stiffness matrix, apply unit deformation at coordinate 2. Apply unit deformation at coordinate 2. Now, what is our coordinate 2? Coordinate 2 is a moment. Okay, so here, this is the first part. Provide fixity, restraint here, then provide restraint here. So first of all, restrain both the part properly, and then apply moment here. How to apply moment? Clockwise. Why clockwise? Because our coordinate 2 is a clockwise. So apply a clockwise moment. Then span will deform. Then in the second part, on the second part, the moment is acting from the top. Therefore, it will be sag like this below. Okay, and then same is to be applied on the second part. So it is moment is acting from the bottom. Okay, so therefore the span first part will going to hog like this. Okay, and what is the magnitude of this? How much magnitude should be? So that when we draw a tangent at this point, which is measuring a slope, this slope must be equal to 1. So how much moment to be applied? Apply such a moment so that the moment this slope will be equal to 1. Then these deformations will produce internal forces in the first part and second part. So calculate that internal forces separately. So part 1 and part 2. Okay, now this is a part 1. Part 1. So part 1 is hog upward. So this is hog upward, and this is slope will be equal to 1. Okay, now to produce, very important, to produce a unit slope here, slope must be equal to 1. To produce a unit slope, how much moment required to apply here? Now it is standard formula. It is 4 EI theta divided by L1, length of the span. But theta is value equal to 1. So how much moment is required to apply here? Simply 4 EI by L1. So in this direction, clockwise direction. Then moment produced at the far end, according to carryover theorem, moment produced at the far end will be always half of this moment. So it will be equal to 2 EI upon L1 in the same sense, in the clockwise direction. Then these two moments will be required to produce a unit slope here. Now this will produce a reactions or a resisting couple will be there. So this is a resisting couple. So since this is a clockwise, resisting couple will be anti-clockwise. So this will be downward, and this force will be upward. And what is the value? It is always M divided by L. Imbalance moment divided by span. So what is M? It is 4 plus 2. So 6 EI upon L1 divided by L1. So it becomes 6 EI L1 square. So this will be the force at this point, and this will be force at the second point. So these are the forces in the first part. Similarly, in the second part, how this deform? It deforms sagging. So it deform downward as shown in the figure. Then this slope will be equal to 1. It will be 1. Again, to produce this slope will be equal to 1. How much force required here? So in the same clockwise direction. So force required will be equal to 4 EI upon L2. And force produced at the far end, it will be equal to half of this. It is equal to 2 EI upon L2. Okay, so clockwise. So now this moment will produce anti-clockwise or resistive couple. So this will be anti-clockwise. So this will be downward and this will be upward. And what is the value? M by L. So 4 plus 2, it is 6 EI upon L2 square. This will be the force at this point and this will be force at the end. These are the internal forces in the part 2. Then we can write the element in the stiffness matrix, column 2. Okay. Now the first is, now to write this element, the basic figure must be in front of you. Just for reference, I will draw this thing. Coordinate 3rd and this is coordinate 4. Okay. Now first element, what is K12? K12 means what? Stiffness at 1. What is coordinate 1? Is a force. This is coordinate 1 is a force, downward force. That means at this particular point, what is the force produced? Okay, so at this particular point, what is the force now? See, this is the force, how much? 6 EI upon L1 square upward. Okay, and this is how much? 6 EI L2 square downward. Okay, one is upward, next is downward at the same location, and L1 is equals to L2. So this becomes 0. So first element becomes 0. Second, K21. So this is 2. Coordinate 2 is a movement. So here at this point, what is the movement produced? How much movement? In the first part, it is 4 EI by L1. And in the second part, clockwise again, 4 EI by L2. So both are producing in the first part as well as second part, both are clockwise in the same direction, assigned direction 2. Therefore, both are positive. So it is 4 EI plus 4 EI L1 L2. It becomes a 8 EI by L1. This is element K22. Next is a stiffness at 3 now. It is a 3-2. It is 3-2. So stiffness at 3 now. What is coordinate 3? Coordinate 3 is this. It is a force. So at this location, what is the force now? So that means consider only the second part. So what is the force now? This is the force. What is direction? Direction is upward now. Direction upward and assigned coordinate is a downward. So this force produced is opposite direction than assigned coordinate. So therefore this force will be minus. So this will be minus here, minus 6 EI upon L2 square. Okay, so this coordinate. So substitute L2 equal to L1. And coordinate 4 is this K42. What is 4? What is 4 is a moment. So this is 4. So here, what is the moment? Moment produces 2 EI. 2 EI by L2. It is clockwise and assigned coordinate is also clockwise. Okay, so it is a 2 EI by L2. Substitute L2 equal to L1. So it becomes 2 EI by L1. So this is the second column of the stiffness matrix. This is the second column of the stiffness matrix. Okay, third element, and this is the fourth. Then we will go for the third column of the stiffness matrix. Okay, then write a command line to generate the third column of the stiffness matrix. Apply unit deformation at coordinate 3. At coordinate 3. Now this is a coordinate 3. Is a force now. Coordinate 3 is a force now. Okay, now in the structure, first of all, provide the fixity. First of all, provide the fixity at the ends of the part. Now, coordinate 3, that means only second part will deform. Since here the fixity is there, therefore first part will remain as it is horizontal and second part will move downward. Only this end will move downward by an amount of delta equal to 1. This will be again fixity. It will remain at the same. Again, so this becomes a level difference, sinking of the support. Okay, so here at the lower end, it is a sagging type. It is 6 EI upon 6 EI delta value 1. 6 formula actually is 6 EI delta divided by L2 square, but delta value 1. So what is the value? 6 EI upon L2 square anti-clockwise. So at the far end again it is sinking moment 6 EI delta upon L2 square delta 1. These are the movements. So it is anti-clockwise. Then to resist this, the reactions will develop. So it will form a clockwise couple. Okay, and what is the value? It is m by l. Okay, so it is a so this is 6 plus 6, 6 plus 6, 12. 12 EI L2 square divided by L. So it becomes a 12 EI divided by L2 cube, and this is 12 EI upon L2 cube. So this is the forces in the second part only. Then we can write the element of the stiffness matrix. Okay. Now to write this element, actually the basic coordinate structures, if it is in front of you, it is very okay. Now first is element 1. What is element 1? Element 1 is a force now. Okay, element 1 is a force. So stiffness at 1. Stiffness at 1. Okay, so here coordinate 1. What is the force generated? It is upward now. It is upward. That is opposite to assigned coordinate. So therefore, it will be a negative. So it is minus 12 EI upon L2 cube. Okay, and substitute L2 equal to L1. Then K21, stiffness at 2 now. Stiffness at 2. What is coordinate 2? Coordinate 2 is a clockwise movement. Clockwise movement. Now here, what is the movement produced now? What is the movement produced here? It is moment produced is an anti-clockwise direction. Moment produced is an anti-clockwise direction. Therefore, this element will be negative. And what is value? 6 EI upon L2 square. So it is minus. Okay, so this is a minus element second. Then next is a K33. K33, that is stiffness at 3 now. So what is 3 coordinate? Is a force now. This is a force now. So here at this location, what is the force now? So it is a, how much force is there? So it is in the force produced is a downward direction, and assigned coordinate is also downward. So it is a in the same direction, therefore it is a positive. That is positive. So it is 12 EI upon L2 cube. So substitute L2 equal to L1. So it is 12 EI upon L1 cube is the third. And then what will be fourth one? Fourth one. So it will be a, what is fourth coordinate? Fourth coordinate is a moment now. Fourth coordinate is a moment. So here what is the moment will be there at this part, at this point, it is anti-clockwise, correct? It is anti-clockwise, and assigned coordinate is a clockwise. So therefore force moment produced will be opposite that of the assigned coordinate. So therefore it is a minus 6 EI upon L2 square, and substitute L2 equal to L1. So it is equal to minus 6 EI upon L1 square. It is equal to 6 EI upon L1 square. Okay, so these are the fourth element of the lying in the third column. Then we will generate the fourth column of the stiffness matrix. Then first of all, right, to generate the fourth column of the stiffness matrix, apply unit deformation at coordinate 4. Okay. Now this is the basic structure. Coordinate 4 is a movement now. Okay, now here at this point, apply a clockwise movement. Then how the span will deform? How the span will deform? Okay, so here first of all, provide the fixity. Here provide fixity here, provide fixity here. So therefore, only the second part will be deformed. Second part will be deformed. And at this point, apply clockwise movement, and therefore the span will be hog like this. And here, how much moment to be applied? So that this slope will be equal to unit. This slope will be equal to unit. Then, okay. Now to produce a unit slope, here, how much moment is required to apply? It is equals to 4 EI divided by L2. Then how much moment will be produced at the far end? Half of this. So it will equals to 2 EI divided by L2, according to carryover theorem. So these are the two moments at the ends. Then this will create what? Resistive couple reactions. So this is a clockwise movements will be developed. then this will be creates a anti-clockwise couple. So this will be downward, this will be upward. Then what is value then? 4 plus 2. It is 4 plus 2, it is 6 EI divided by L2 upon L2. So it will be equal to 6 EI upon L2 square. So this will be 6 EI L2 square, and this will be upward 6 EI L2 square. Then write the coordinates in the element. Then first is first element, second element, third element, and fourth. This is our first element. First element is downward. First element is a force now. So first is K14. K14. So that is stiffness at 1 now. So at 1, that means here what is the force? At coordinate 1, what is the force? So it is a downward force will be there. So downward, that means in the direction of assigned coordinate. So how much is the force? Plus 6 EI upon L2 square. This is the force produced. Okay. Then stiffness at 2 now. What is coordinate 2? Coordinate 2 is a movement now. Coordinate 2 is a movement, clockwise movement. Here the movement produced is also a clockwise. So it is plus. And what is this value? 2 EI upon L2. Okay, so second element is plus 2 EI by L2. Then K31, that is stiffness at 3 now. So what is 3? So what is coordinate 3? Is a force now. Coordinate 3 is a force now. So here at what is the force produced? How much at this point? What is the force produced? It is 6 EI upon L2 square. But it is upward. Okay, it is upward, and assigned coordinate is downward. So therefore this will be minus. So it is minus 6 EI upon L2 square. Then substitute L2 equal to L1. Okay, so this is third element. And what is stiffness at 4 now? K44. So our coordinate 4 is a movement. Okay, it is clockwise movement. So here how much movement is? It is a clockwise. So therefore plus it is 4 EI by L2. So it is 4 EI by L2. Substitute L2 equal to L1. So it becomes a 4 EI by L1. So this is the fourth column or final column of the stiffness matrix. Then write in all the elements in the matrix form. So it is a K matrix will be equal to, now these are the, this is all the elements are in the fourth column. So you will find here, it is in the fourth column. So write in the same sequence. Okay, similarly, other elements are as shown in the figure, as shown in this matrix. This is the first element, second column, third column, and this will be fourth column. Okay, so here common part is EI by L1 cube. Okay, so we can write, we can take this EI into L1 cube common outside also. Then just check the properties, whether it is correct or not. So what is the first property? Stiffness matrix is the square matrix. So is it square? Yes, there are 4 columns, 4 rows. First property satisfied. Second property, it is a symmetric matrix. Okay, so this element, so which element it is? K21 is equals to 1, 2. Then this element, K31 is equals to 1, 3. Element is same. Then this is a K41 is equals to 1, 4. These elements are same. Again, this element K, what is this? It is K42 now. Fourth row, second column is equals to this element. Then this element and these elements. Okay, then these elements and these elements. Okay, so therefore it is a, all the elements, that is, it is a symmetric matrix. So second property is also satisfied. And third property is that the elements lying in the leading diagonals are positive. That is K11, K11, K22, this is K33 and K44. It is always positive. Now here in this diagonal, all the elements are positive. So therefore, generated stiffness matrix is a correct one. Okay, so this is a second part of this stiffness matrix chapter. Now in the third part, I will explain how to do the analysis by using stiffness matrix method. Thank you.